Hello everyone, my name is Rongxuan Gao. I used to be a master's student from the University of Tsukuba and a research assistant at AIST. Here I'm glad to have this opportunity to present our work. The topic is hybrid modeling and predictive control of large-scale cloud movements in neural network. My presentation is divided into 5 parts. The first one I'd like to introduce is the background of our research. Our research area is cloud management. This is a more comprehensive concept than cloud control. Cloud management procedure involves event planning, staff training, cloud control, and data collection. In history, the causes of many cloud disasters are surprisingly similar. That is, pedestrians crowded the roads. Therefore, it's necessary to apply cloud management in large gatherings to prevent the occurrence of accidents. Intelligent transportation systems should be a well-known field and guide the future direction of intelligent urban development. Cloud management is supposed to be one of the key components of the field. However, the component has been overlooked by the scientific and the industrial communities. The literature providing this view was published in 2019. The fundamental limitation of the field lies in the lack of an intelligent cloud control framework. So, in this work, our research goal is an intelligent framework for large gatherings in urban neural networks. I think we need to get a general image of what cloud control actually looks like. Look at this example. The coordinated control of cloud movements is highly dependent on the manual commands from traffic guards, such as forward, stop, and speed flow. Among these commands, the speed flow commands have a practical value of dispersing the congestion pressure in a neural network. The use of speed flow commands can result in increased or decreased flow in downstream streets, causing discrete changes in the number of pedestrians. Next, I'd like to present related work in a limited amount of literature on cloud control in neural networks. We found a particularly clear division. One part tended to study cloud control strategies for emergencies. For example, Lei et al. Studied emergency evacuation strategies in large gatherings, but they did not verify the effectiveness of their method in large instances. Taneja et al. Studied a method to fully utilize the available capacity of the network. The shortcoming of their method is that it cannot handle dynamically changing demand. Another part of researchers turn to develop cloud control strategies for non-emergencies. The method proposed by Li et al. Has a limitation of huge computational burden in large instances. Shigenaka et al. Did experiments with large-scale examples, but the computational cost of their method is very expensive. The cloud control problem is indeed very complicated and difficult to trade off between the system identification and the limitation of the computational burden and the controller synthesis. Therefore, it's necessary to develop a dynamic cloud control strategy. In fact, model predictive control has a high potential for application in the field of cloud management. For more complex, large-scale cloud control scenarios, using a microscopic model that treats clouds as a follower of densities is a solution. So next, I'd like to introduce a well-known microscopic modeling approach in the field of transportation, the SFM. SFM models a row network of oversaturated synchronized intersections to calculate the traffic flow dynamics in row networks. In the field of transportation, SFM is used not only to handle coordinated control in heavily congested urban networks, but also to estimate the dynamics of pedestrian queueness. SFM is concise enough. It purely contains continuous state and control variables to greatly simplify traffic flow dynamics. However, it's impossible to directly use SFM in our research because SFM cannot observe the discrete dynamics of traffic flow. SFM is unable to model road networks with rich travel routes. Our work is inspired by the SFM-based methodologies to develop a framework for controlling large-scale car flow in urban road networks. In addition, we want to overcome the limitation of SFM so that it can express the hybrid dynamics of car movement in road networks. In the next part, I'd like to introduce a prior knowledge about the classic SFM. Let's consider a generalized link Z with an upstream synchronized intersection J1 and a downstream synchronized intersection J2. Then, the traffic flow dynamics of link Z from the control interval Kt to K plus 1t is expressed as a formula in the middle of the slide, where t is the length of control interval, k is a discrete time index, x subscript z denotes the number of vehicles in link Z. The first term in the bracket is the inflow of link Z, while the second term is the outflow of link Z. E subscript Z is the disturbance of link Z, which is numbered by the demand D subscript Z, and the exit follow G subscript Z. Let's focus here on how the inflow and outflow are calculated. The inflow is a cumulative sum, and the cumulative item is the maximum outflow of the links W of the set I subscript J1, multiplied by the turning rate tau subscript WZ, and then multiplied by the signal of the intersection J1. The signal is equal 0 or 1, corresponding as a control signal to allow or prohibit the movement of vehicles. The outflow is expressed as the maximum outflow of link Z multiplied by the signal of the intersection J2. The number of vehicles in link Z must satisfy the limits of the link capacity C subscript Z, and we use the Boolean domain B to denote the boundary condition of the signal of each intersection. Extending the formula for the traffic flow dynamics of link Z to all network links will generate the matrix expression at the bottom of the slide. We will conceptualize our modeling approach to compute cloud dynamics based on the classic SFM, which we will call a cloud dynamics modeling. The figure at the bottom of the slide illustrates the concepts of our model. We circle the range of the road network with an ellipse. The network is a collection of directed links. The network links are denoted by arrows and the intersections by dark circles. We divide links into internal links, entry links, and exit links. The internal links start at their upstream intersections and N at their downstream intersections. The entry links have no upstream intersections but have the exodus arrivals D subscript D, whereas the exit links have no downstream intersections but have the internal departures G subscript D. Here, the differences between our modeling and the classic SFM is that we consider introducing a speed flow signal delta subscript J for each intersection. The speed flow signal is a discrete command, and its function is to change the proportion of pedestrians from the upstream links to downstream links. For example, when the speed flow signal of the intersection J1 equals 1, then the proportion of pedestrians from link W1 to link Z is 50%, and the proportion of pedestrians from W2 to Z is 100%. At the next moment, when the speed flow signal equals 2, the proportion of pedestrians from W1 to Z becomes 100%, and the proportion of pedestrians from W2 to Z becomes 0. So we need tau subscript WZ delta K instead of the fixed turning rate tau subscript WZ. We re-express the in-follow and out-follow of link Z as the formulas in the center of this page. The in-follow is the minimum between the maximum number of pedestrians allowed to follow into link Z and the current accumulated number of pedestrians in the upstream links of link Z. The out-follow is the minimum between the number of pedestrians allowed to follow out link Z and the current number of pedestrians in link Z. What needs to be mentioned here is that we replace the saturated follow S subscript W and S subscript Z in the classic SFM with the concept of crowd follow rate. The crowd follow rate reflects the actual crowd follow per unit egress width of the link. In this paper, we used a convenient method to estimate the crowd follow rate by multiplying the average crowd density in the link by the average speed of crowd in the links, and then multiplying by the egress width of the links. Because we introduced the speed flow signals to the classic SFM, then the crowd dynamics of the network are described by a combination of the ordinary differential equations and discrete switching events. We consider a set phi of all combinations of the speed flow signal vector, and the matrix B is parameterized by the index lambda of the set 1, 2 to an absolute value of 5. So the crowd dynamics of the network is expressed as the form at the bottom of the slide. We then integrate the crowd dynamics modeling into the MPC framework. In this study, we simply applied MPC. So here, in this slide, I just describe the settings of the objective. We refer to the literature in the field of transportation and set the goal to balance the occupancies of the road network and to reduce the risk of spillover of the crowd in the road. Thus, the diagonal elements of the matrix Q are set equal to 1 in the capacity C subscript Z, and the matrix R is defined as the lowercase r multiplied by the identity matrix I, where the lowercase r is a very low scalar weight. The next part describes the experiment. We used a large-scale crowd control scenario of an annual fireworks festival in Japan as an experimental case to verify our framework. The figure shows the raw network structure of the event. We marked the origin and destination of the crowd movements in the figure. The square markers show the locations of speed flow signal, and there are 2 places in total. The standard signals are responsible for controlling the movements and stopping of the crowd. They are represented by circular markers in the figure. From the origin to the destination, pedestrians will pass a total of 7 standard signals. The data we measured for this event include the demand data at the origin, the railway timetable, the capacity of each train, the control instructions issued by the traffic guards, and the geometric parameters of the raw network. In this case study, the speed flow command contains two types of commands. We use blue to represent the speed flow command 1 and the origin to represent the speed flow command 2. When the speed flow signal of intersection A is blue, then a half of the crowd in link 1 goes to link 2 and the rest to link 5. When the signal of A is orange, then all the crowd in link 1 goes to link 5. When the speed flow signal of intersection B is blue, then all the crowd in link 5 goes to link 6. When the signal of B is orange, then all the crowd in link 5 goes to link 8. Therefore, there are 4 options for the working route in this case. Because it's difficult to have the authorization to do real experiments, we used a multi-agent pedestrian simulator called CrowdWalk to conduct the experiments. The figure shows the visual interface of a CrowdWalk. Green dots in the simulator's screen indicate the moving pedestrians, and red dots indicate the stopped pedestrians. The positions of the standard signals are marked with red circles, and the positions of the speed flow signal are marked with blue circles. To reproduce the large-scale car movement scenarios based on our data and cities, and this simulator, we applied the data simulation technique used in our previous work. Then, we implemented the MPC framework on this simulator for experiments. 2 additional points need to be made regarding the detailed setup of this experiment. First, when the crowd is stopped by the signal, we cannot estimate the speed of the restarted crowd follow, and then we can't calculate the crowd follow rate. So in this experiment, we assume that the speed is half a value of the maximum speed. Finally, the dynamics of link 1 is unpredictable because our demand data only contains information about the number of departures and the departure time. Therefore, the core dynamics calculation of link 1 was omitted in the experiment. We consider two evaluation methods for evaluating experimental results. One is the maximum value of the percentage of pedestrians at each link during the simulation period. Another is that we use sigma k to evaluate whether the distribution of the crowd is balanced in the network. The distribution is balanced best when the value of sigma k is equal to 0. With our MPC framework, the 2015 experiment was performed smoothly while there were 2 and 5 invisible issues occurred in the 2014, 2017, and 2018 experiments respectively. Based on criterion 1, the table on this page summarizes the maximum occupancy rates. We highlighted the value where the maximum occupancy rate was above 0.9, meaning that the link is heavily saturated. The presence of a value slightly larger than 1 is caused by the compression of the distance between the agents. The results show that our framework plays a powerful role in reducing link saturation. It also implies that the performance of our framework is related to the link length, route distance, and demand. Based on criterion 2, the figure in this page depicts whether the curve distribution of the entire network is balanced at every moment. Our MPC framework is significantly superior to the manual control simulator. The results provide confidence that the demand significantly affects the upper limit of our framework performance. Comparing these results as to why the 2015 results were so lucky, we speculate that this is due to its relatively low demand. Finally, I'd like to give a conclusion and some discussion of our framework. In this study, we proposed and integrated a hybrid modeling of cloud dynamics into MPC to control large-scale cloud movements in road networks. According to the experimental results, our proposed framework is capable of controlling the scenario of a map with variable working routes. This shows in this case that, following the underlying definition of SFM, the method framework of the SFM-based methodologies in the field of transportation is also effective to achieve the desired results in a problem of controlling large-scale cloud flow in a hybrid dynamical scenario, because the resulting framework works well to ease and balance the congestion burden on the road network. To our knowledge, none of the existing cloud control work can provide a solution to the problem of large gatherings involving hybrid dynamics. However, our framework has shortcomings that need to be improved in future research. Here we summarized 2 points. First, the estimation method of the cloud follow rate was too rough. And finally, neither the manual control nor our framework was fast enough to cope with the pressure of the sudden increase in demand. That's all for my presentation. If you have any further questions or need some help, such as the open source of our code, the animation of the simulation, or details of this study, or our other studies and research collaboration, please feel free to contact my master advisor, Dr. Onishi. Here is his email address. Thank you.